Okay, so I have handed back your test and we are going to take a minute to go through that in just a second. In the meantime, I do want to remind you that you have several things on active chemistry. You have several things on active chemistry, one of which is due tonight. So make sure you take a look at that. That covers the material we covered early in the week on making solutions. And then the ones, homework 11 and 12 are covering some of the newer material, but they're not due until after spring break. And then at the end of spring break, that Monday night, I will have a math foundations assessment. Is it a quiz?
Yeah,
It's a quiz. Okay. Yeah. So quizzes are not automatically attached to your grade. And then, so I'll just see that, yes, you did the assignment and I'll give you credit for it. Okay. So just kind of have those things on your radar. I know it's several different assignments, but you do have quite a bit of time to do them. And I've tried not to make things due the Sunday night of spring break, just in case, you forget. So I wouldn't encourage you to put it off, but if it happens, you'll be okay. All right. So questions about that? So we are going to have some different ways that we do calculations for concentration. Okay, so we already know about molarity. We've used this quite a bit. So molarity is the moles of the solute divided by the liters of the solution. This is really very convenient for lab because we have volumetric class, so we just put a certain mass or a certain amount into the volumetric class, fill to the line, and boom, we've got molarity. The problem with molarity is that because volume will change slightly as I change the temperature, then I'm going to have a different molarity for the same substance as I warm or cool it. Most of the time, we don't need that kind of precision in lab, so we don't worry about it. But if we need something very precise, we're going to need a different kind of calculation. So the next one we're looking at is molality. Now, molality, notice, is also moles. The names are really similar, molarity versus molality. Molarity is per liter of solution, so total on the bottom. Molality is per kilogram of solvent. So that means if I have an aqueous solution, it's not the kilograms of everything, it's just the kilograms of the water. Usually the amount of solute is pretty small, so it wouldn't really affect our calculations. But if you take something like sugar, where you can have a 6 molar, 10 molar, 15 molar solution, the mass of that sugar can really be a lot more than the mass of the water. And so there's a big difference between molarity and molality. Okay. So we're most concerned with molality of all of these in this chapter because we're going to use it in the calculations for freezing point depression and boiling point elevation. You'll do a lab with that after spring break. For mass fraction or percent, sometimes this is called parts by weight or parts by mass. You're basically just taking the mass of whatever part you're looking at, and it doesn't have to be the solute, but it could be. So the mass of the solute divided by the total mass. So if I have a salt solution, the mass of the salt divided by the mass of both the salt and the water, okay? So molality is the only one where the bottom isn't the total. I could also do a volume percent that is less common, but one place you do see it is with rubbing alcohol. So if you buy rubbing alcohol at the grocery store, it usually says 70%. That means that they have 70% of it is alcohol and 30% of it is water by volume, as if they had taken, 7 liters of one and 3 liters of the other and mix them together. The reason that's not used really commonly is that volume is not conserved, which means that I could take those two things and mix them together, and instead of ending up with 10 liters, I might have 9.5 liters, or I might have 10.5 liters, depending on the attraction of those particles to one another. Since alcohol and water have similar interparticle forces, there's not much of a change, and so that's why they use that. All right, so the next one is mole fraction, and mole fraction is just doing moles. We're not going to go anything with liters or mass or anything like that. Convert everything to moles. Top part is the thing we're looking at, so say salt. Bottom part is the total. And the nice thing about mole fraction is that you can use it with gases, where with gases, because they're miscible, you don't really have one thing is the solvent and one thing is the solute, and you might have several gases together. So we might have oxygen and nitrogen in our atmosphere, but we know there's also water vapor, and we know there's also carbon dioxide. So we can find the mole fraction of each of those. We used that a little bit last semester. That is represented by the letter X, and then we use the subscript to identify which of those things that we're looking at. And then we could also look at parts per million, parts per trillion, parts per billion. Each of those.
Quadrillion if you really wanted to.
Say again?
Parts per quadrillion if you really wanted to.
If you really wanted to. These are commonly used with things that you don't want in the water, but you just can't get everything out of the water. How much lead is in the water? How much iron is in the water? So something that you're less concerned about, like copper or iron, you might measure in parts per million. And then something you're more concerned about, like arsenic, you would measure in parts per trillion, because you want there to be very, 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 very few atoms of arsenic. Generally, what you use with that is the mass. So you take the mass fraction, only instead of multiplying by 100 to get a percent, you would multiply by 1,000,000 or 1,000,000,000 or 1,000,000,000,000. Yeah.
I was just gonna say that, like, when the train derailed,
In Ohio,
they measured everything in parts per million, like the surrounding area that felt it was
exactly. So if you had heard much about the train wreck, first one, I think they said there's been like 5 in the last several weeks, but in any case,
One, and they audit them all the time, but that one had a lot of blood.
yeah, that one had a lot of chemicals that were unpleasant. And so they, as they reported on it, they were reporting how much was there. Now, something that you normally, like arsenic, you might want to report in parts per trillion. In a case like that, they might have to report it in parts per million because the amount would be so high because of. Okay, so I'm not going to walk through this calculation because we've done this before, but just remember that molarity, we use a capital M to express molarity, because molality also is going to use an M, but it's going to be lowercase. We use concentrations expressed in moles per liter, and those units tell us how to do that calculation, moles divided by liters. So if I had a question like this, when 5.85 grams of sodium chloride are dissolved in 1 liter of water, what is the molarity of the solution? Can I take that 5.85 and just divide it by the liters?
No, it's grams.
Because it's in grams, we would need to convert it. So I was hoping to have enough time that we could work through some of these calculations, but we would look up on the periodic table molar mass of sodium and molar mass of chlorine, find that combined it's about 58, and then we would take, and that's why I picked that number. So if we take 5.85 grams divided by 58, we find that we have about 0.1 moles. 0.1 moles divided by 1 liter gives us 0.1. And you can either write moles per liter, or you can write that capital M. Either way works. Okay. What I want to get to is how to calculate some of the other things. Let's see where we are. Okay, so we talked about parts by mass, is sometimes called weight percent. I'm not going to go into that because we don't use it a whole lot. I might talk about it in more detail after spring break, but let's do mole fraction. Okay, so mole fraction represented by the letter X. So this is similar to a mass fraction in that we're doing the part over the whole. But because this isn't a percent, we're not going to multiply by 100%. So this is just one of those quirky things that when chemists were starting to develop these formulas, this one they just left as a decimal. Others they put into a percent. So we just leave this as a decimal. So let's take that same solution where we had 5.85 grams of salt, sodium chloride, in 1 liter of water. So we already know that we had 0.1 moles of the salt. We would need to find the moles of the water. So what we would do in class for this is we would say, okay, well, if I've got 1 liter of water, the density of water is about what? 1.0. Now that is going to change with temperature. It's slightly less at room temperature, but not enough to make a difference in these calculations. So we're going to assume that we have 1 kilogram of water. So 1 kilogram of water, or 1,000 grams, divided by its molar mass. So this is where this number comes from. We took 1,000 grams divided by what's the molar mass of water?
It's 18.
18. So we use that a lot. But if you didn't remember, you can look it up. 16 for oxygen, 1 for each hydrogen. That gives us 18. So that 1,000 divided by 18 gives us this number here. So I have 0.1 moles and I have 55.5 basically moles. Total, that's going to be on the bottom, and the 0.1 is going to be on the top. So my fraction will be 0.1 divided by 55.59. And then this would be my mole fraction. This is rarely used with aqueous solutions. It is more used when we have vapor involved. Either we have gases or we have a liquid like water whose vapor pressure we want to measure, in which case we would be more concerned with what's the mole fraction of the water than the mole fraction of the salt. So we could go through that calculation, or we could just subtract off. We could say, well, if the whole thing is going to be 1, I could take this number and subtract it from 1. So these two things, 0.0018 and 0.9982, those should add up to 1. Okay. We good on this slide? Okay, so like I said, we use this with gases. We talked about this a little bit in the gas chapter last semester. So when we are trying to find the partial pressure, and remember in Henry's law that we talked about on Wednesday, we use the partial pressure. To find the partial pressure, we have to take the pressure of the whole gas, atmospheric pressure, and then multiply it by that mole fraction. So if our whole pressure wasn't actually 1 atmosphere, if our whole pressure was actually 0.95 atmospheres, and we wanted to find the partial pressure of the oxygen, then we would need to multiply that decimal that we had used on Wednesday, which was 0.21, times that. So the formula looks like this. The partial pressure of gas A is going to be equal to the mole fraction of gas A. So the subscripts are telling us what substance are we talking about times the total pressure. The same thing from chapter 9 last semester. And so if we were looking at the solubility of oxygen in water from atmospheric conditions, we're going to assume our mole fraction of water is 0.2. So we need to find the partial pressure of oxygen. And this is where I said sometimes my older slides have S instead of C. So we said for Henry's Law, we used C, so we don't confuse it with entropy. I'll change this slide before I upload it. But we're going to take the mole fraction here times the atmospheric pressure. This is going to give us the partial pressure of the oxygen. And then what is this? If I'm talking about Henry's Law, what's the 1.28 times 10 to the minus, what is that, 3?
That's the solubility.
That's the solubility constant.
Yeah.
Okay, so at room temperature, that's how, the constant that tells us how much oxygen will dissolve in water. But if I have, instead of 1 atmosphere, maybe I have 1.5 atmospheres. I've got a pressurized room. That's going to increase. So sometimes hospitals, and I've actually been to an equine hospital, uses a bariatric chamber. So the bariatric refers to the bars, which is a measure of pressure. They will bring the horse into this chamber, and then they will increase the pressure of the oxygen so that the more of the oxygen is being absorbed into the horse's bloodstream and cells to promote healing. Now, you can't live in that environment if you stay too long, it would be bad for you. But for a treatment of an hour or two, it's very helpful. Okay, so if I plug all that stuff in my calculator, I end up with a solubility of 2.56 times 10 to the minus 4 moles per liter. Moles per liter, those units, what concentration is that?
Molarity.
Molarity. All right, are we good with this slide? Okay, molality. So molality is not as simple as molarity for the lab. We talked about that a little bit. We said that the reason why we might want to use molality is it's going to be more precise because the temperature may change the volume, but mass does not change with temperature. Mass is conserved, so molality uses the mass of the solvent, and regardless of the temperature, we're going to still have the same concentration, the same numerical concentration. And we're going to make a point of remembering that for this one measure of concentration, we don't have the total on the bottom. We just have the solvent. Usually the solvent makes up the vast majority of the mass, but not always. So that's why you got to pay attention to that. Okay, so let's try a calculation. For dilute aqueous solutions, so dilute meaning not very concentrated, usually the molarity and the molality are pretty close because the mass of the water is pretty darn close to the volume of the water. The density of water is 1, and the moles of the solute is pretty small compared to that. But if I'm not talking about a dilute solution, or if I'm not talking about an aqueous solution, this doesn't necessarily apply. Okay, so now let's look at a situation where we have 2.43 grams of glucose dissolved in 563 grams of ethanol. So are either of these numbers in the units that we want for molality? Not quite, it's close.
Grams.
Yeah, it's in grams, we want it in kilograms. So pretty easy to switch it over. What are we gonna have to do with glucose?
Change it to moles.
Change it to mole, so we're gonna need the molar mass. And that's gonna be about 180. I will leave it to you to verify that, but I trust that you know how to make molar weight calculations. Okay, so I'm gonna take my mass, and am I gonna multiply it by that number or divide it by that number?
Divide.
Divide. I need to get moles on top. Right now my moles is on the bottom, and I need to cancel my grams. So I'm going to divide by the 180, and that's going to give me 0.01349. Okay, so as you're copying down notes, if you don't remember which way to do this, you might write down, in addition to writing down find moles of glucose, put divide mass by molar weight, so that you remember how to do that when you're trying to do your homework. Okay, so then we've got moles, and then we're going to divide it by kilograms. We get the kilograms by just moving that decimal over by 3, so it is 0.563 kilograms of ethanol. So I'm going to take my 0.013 glucose divided by my 0.563 kilograms of ethanol, and that's going to give me 0.0240. Okay, now why do I have that 0 at the end? Why didn't I just leave the 0 off?
Significant figures.
Significant figure. So remember, your calculator may chop off a 0 if it comes to an exact number, but we are not going to drop zeros if we know that we need a third significant figure. Why don't these zeros count as significant figures?
They're before the number.
They're before the first non-zero, okay? So left hand or leading, we lose them. All right, so that's how we find molality. All right, so I'm going to show you this example. We're not really going to have time for you to process this, but I want you to be aware of it so that when you're looking at your homework that you've got that second example that you can refer back to. So in this case, we've got propanol mixed with water. We're going to assume water has a density of 1 gram per milliliter exactly. And if we do the calculation for it, we are going to have to turn the grams of propanol into what? Moles. Moles, yeah. So if we want to know the molarity or the molality, we need the propanol moles, right? Now for the water, we don't need that in moles for these two, but it also says find mole fraction. So we would have to convert it to moles for that. Okay, so you can practice each of these calculations and then verify that you come up with those numbers. Okay. All right. Have a lovely spring break, but please make sure you are well rested as you drive. No car crashes. Please do not take extreme chances with yourself or with others. Stay sober while you are in the control of the vehicle. Come back not next Monday, the following Monday. I really want to see you again. Yeah. I don't know how that happened.
Yeah.